In this class, we can see one problem related to step matching. How we can design a single step using Smith chart. So first, we need to recall the steps behind this design. So first, we need to find the normalized impedance that we done previously. So how we can find the normalized impedance means you have the load impedance and the characteristic impedance. You just divide the load impedance with the characteristic impedance, then you will get the normalized impedance. So after getting this normalized impedance, you can easily plot this normalized impedance in the Smith chart, where the real part of this normalized impedance represent the R circle value and the imaginary part represent the reactance value. So you will get that point. After finding that point, to design the single step, we are designing parallel steps. We know that the single step is a short transmission section which is connected parallelly with the main transmission line. So here we are taking the parallel connection. So it's better to represent this terms, all the terms in admittance rather than load impedance. So we need to find the admittance. So after plotting the normalized load impedance, then find the normalized admittance. For that, you can just draw a straight line to the origin from this point, from this normalized impedance point, and draw a circle taking the radius as that normalized impedance distance. Then you can extend that straight line to other half of that circle. Then the meeting point of that circle to the straight line is the normalized admittance. So after getting the admittance, we need to find where is R equal to 1 circle, or in terms of admittance we can say that G equal to 1 circle. So you can find where is G equal to 1 circle or R equal to 1 circle. Then you find the meeting point of this R equal to 1 circle and the VSWR circle. So first circle that we drawn to find the normalized admittance, or find the circle that drawn using the radius of normalized impedance, that is called VSWR circle. So now you find where this R equal to or G equal to 1 circle meet with the VSWR circle. You can point that as A and B. So that's the location, that's the point where we need to design the steps. So after getting this, you can find the step admittance. So that meeting point, what is the reactance value, reactance circle value, that should be the step admittance. So to get the admittance, that should be normalized value. So get the admittance, you should multiply that with y0 or 1 by z0. So that way you will get the normalized, that way you will get the step admittance. So next we need to find the distance between the step and antenna. So now you located the meeting point of R equal to or G equal to 1 circle with the VSWR circle. We marked it as A and B. Then this the distance from this YL, that means load admittance, to that point in clockwise direction is called the distance between the step and the antenna. That means distance between the load and the step. Next we need to find the step length. That is the only in single step matching we have two design criteria. One is distance between the step and antenna, and another one is the step length. So now we found how we can now we found the distance between the step and the antenna. Next we can find the step length. So to find the step length, you can extend the reactance step admittance value, admittance circle to the outermost circle. That means first outermost circle. Then you can measure the distance in anti-clockwise direction from PSC to that point, will represent the step length. So we can see how we can find this by checking one problem. So we can directly move to our problem. An antenna with an impedance of 40 plus J30 ohms to be matched to a 100 ohm lossless line with a shorted step. Find the required step admittance, the distance between the step and antenna, the step length, the standing wave ratio on each segment of the system. So our question, we have an impedance and we have a match to a 100 ohm lossless line. So we need to design a step, single shorted step. So we can see the steps. So first we need to find the normalized impedance. For that we can divide the ZL with Z0, that is 40 plus J30 divided by 100. You will get 0.4 plus J 0.3. So you just check where is R equal to 0.4 and J equal to 0.3. So that point is, we can find that point is here. So this point represent J equal to R equal to 0.4 and X equal to 0.3. Then we can draw a straight line to the origin. Origin means here R equal to 1 point. R equal to 1 circle is the origin. So we can draw a straight line to this origin. Then take the that as radius, that means from O to this point we can mark it as P. Then take OP as radius and draw a circle. That circle here, it is blue, represent that circle, and that circle is called as VSWR circle. Then this straight line we can extend just opposite to that circle. So from this point P to O, then O to P dash we can extend. So this point is ZL, normalized impedance, and the extended point somewhere will meet this blue circle, and that point is the YL, normalized admittance. Now we are taking only this normal. Now all the calculations is based on this normalized admittance. So now we found normalized admittance. Then first we need to design the step. So to design the step, our first question, we need to request step admittance. So first we need to find the step admittance. Before that we can see that this YL is, you find the R circle value and H circle value at this point YL, that means P dash. Then you will get the normalized admittance as 1.6 minus J 1.2. Then from this we can check this whether it is correct or not by using the equation. We already found ZL, then find the inverse of ZL. This you will get it as 1.6 minus J 1.2 itself. Then to find the normalized impedance, you can multiply this is the normalized value. Then to obtain the real admittance value, you can multiply this with 1 by Z0. So that's the normalized, that this is 1.6 minus J 1.2 is the normalized load admittance. Next we need to design step admittance. So we can see how we can design the step admittance. For that, after drawing this VSWR circle, you check where is R equal to 1 circle. So if we are saying in terms of admittance, you can check G equal to 1 circle. R equal to 1 circle is same as that of G equal to 1 circle. So this represent R equal to 1 circle. So this one represent R equal to 1 circle. Then you find where this R equal to 1 circle meet this blue circle, that means VSWR circle. So this point A as well as this point B, these 2 points, the circles meet this VSWR circles, and R equal to 1 circle meet this point A and this point B. So we can find the step admittance by looking what is the reactance circle at that point A and this point B. So this is plus or minus, same value should be there. So find what is the reactance circle value at the point A and B, that should be plus or minus a reactance value. So here it is plus or minus 1 point J 1.04. So this is the normalized value. So to get the real value, you should multiply it with 1 by Z0 or Y0. So you will get it as plus or minus J 10.4 millisiemens. So that is the required step admittance. Next we can see how we can find the distance between the step and the antenna. It's very easy. After getting this point A and B, you just measure the distance from this load admittance, that is we marked as YL previously, from that YL to this point B as well as this point A in clockwise direction. So here we can see that LB and LA is marked. So from this load admittance point, measure the distance from load admittance point to this point B as well as this point A. We have 2 points always. So find what is LA and what is LB. So to find this, you can measure the angle. So here from this second circle we will get the angle easily. So from this angle, first you measure this angle directly, then convert that angle to lambda terms. For that, multiply and divide a lambda term with this obtained angle. Then multiplied lambda we are keeping as itself. The divided lambda we are converting as 720 degree, because 1 lambda is 720 degree in this Smith chart. So this obtained angle divided by 720 degree into lambda will be the distance from YL to this point B as well as this point A. So we can see how much we got here. So LA is 0.36 lambda and LB is 0.032 lambda. That means LB is from this load YL to this point. So you find what is the angle between these 2 points, then convert that into lambda. Then YLB is from this load admittance to this point A. So for that we can see that this total is 360 degree. So if it is 360 degree, then we can easily find by measuring this 360 degree minus this distance. So this is total of 360 degree. 360 degree means lambda by 2. It corresponds to lambda by 2. So lambda by 2 minus this distance from this PSC point to this distance is the total distance LA. So this way we can find the step distance from load. So that's the step. Then next we need to step distance and step length. We now found step length. Next we need to find the step location. Step distance from the antenna, that means step location we found. Next we need to find the step length. So the distance between the step and the antenna is the step location itself, and next we need to find the step length. So what is the length required for this step? So we need to connect a step at a distance of what? At a distance of 0.36 lambda or at a distance of 0.032 lambda. Then what is the step length needed in that location we need to find. So for that it's easy. You just extend that reactance circle what you obtain from this point B and A. You just extend that reactance circle to this outer point and this outer point. Mark it as B dash and A dash. From this origin you can extend a straight line to this A dash and this B dash. After extending a straight line to A dash and B dash, you can measure the step length from PSC. This point is PSC in anti-clockwise direction to B as well as A. So we can see that this measurement we can see from here PSC, or we can measure this distance in clockwise direction also. So from this point PSC to A dash and this PSC to B dash we can measure the distance. So that is DA and DB. So from PSC to A dash is represented as DA, and from PSC to B dash represented as DB. If it is measured in anti-clockwise direction, the distance mark should be reversed. So the distance to A dash is measured as DA, that is from PSC to this point clockwise direction, and the distance to B dash is measured as this distance from PSC to this point in clockwise direction. That point is DB. So you remember that here we marked as A, we extended this point as B dash. Then here we marked as B and we extended point marked as A dash. That's why this distance is DA and DB in clockwise direction. If you are measured in anti-clockwise direction, this distance should be DA. This distance should be DA and this distance should be DB. So that's the difference. So this way we can measure the step length. So you can follow the clockwise measurement. In that time you can remember that if you mark here as A, then this should be B dash, then this dB should be this distance, and if you mark it here as B, then this should be A dash, and this distance should be D. So you can follow this clockwise direction, and that's only difference. So we can measure the distance. So you can measure the angle from this PSC point to this point, then convert that angle into lambda terms. For that you can multiply a lambda and divide a lambda. So that divided lambda you can convert to 720 degrees. So this angle is only 88 degrees. So 88 degree divided by 720 degree into lambda should be dA. Then dB is the angle from this point to this point A. This point B dash, the angle is 272 degrees. So 272 degree divided by 720 degree into lambda. So you will get it as 0.3778 lambda. So if you added these two terms, you will get it as lambda by 2. So that is the cross check possibility of cross checking these two distance. Then we need to find the what VSWR. That's our fourth question. We need to find the VSWR. So VSWR means the value from, we will get this VSWR circle meeting point on x-axis. So that is here 2.7. So this is the standing wave ratio on the line segment between the step and the load is equal to 1 to the left of the step because the line is matched, and is equal to infinity along the step because the step is shorter. So this way we can design a step. So remember the steps. First we need to find the normalized impedance. Then after getting the normalized impedance, we can mark the normalized impedance on the Smith chart. Then you draw a straight line from that point to origin and extend that straight line to other half of the Smith chart. Then draw a circle taking radius as this OZL, then or this point if it is P, then OP, then draw a circle, then check that straight line, extend a straight line where it meet with this VSWR circle, and that point admittance is the load admittance. Then after getting the load admittance, first we can decide the step admittance. So to decide the step admittance, next you check where is R equal to or G equal to 1 circle, and where it meet with the VSWR circle, mark it as A and B. Then after marking it as A and B, you can mark it as P and Q, etc. So after marking it as A and B, then we can find the step admittance by checking what is the reactance circle at point A and B. So that is the step admittance. The value should be in normalized. So to find the normal value, you should multiply it with Y0 or 1 by Z0. Then after getting this, we can find the step location or step distance. So after finding this A and B, it is easy to find the step distance or step location. You measure the distance from YL to B and YL to A. So to find that distance should be in lambda terms. So to find that, first you measure the angle between this YL and B and YL and A in clockwise direction, then multiplied and divided lambda with that angle, then divided lambda we are converted as 720 degree. So this degree cancels, so you will get the value in lambda. So you will get LB and LA. Then after find this LB and LA, one more design criteria is step length. So to find the step length, you just extend that X circle to this point A dash and to this point B dash. So the extended circle point from A to extended point is B dash, and from the point B, the extended point is A dash. Then draw a straight line from that point A dash and B dash to draw a straight line from origin. After getting that A dash and B dash, you measure the distance from PSC, short circuited point, to A dash, and that is the distance between distance of step length at A, that is dA, and you can measure the distance from PSC to B dash, that is dB. So that also in clockwise direction. You can also measure that in anti-clockwise direction. Then you will measure, if it is in anti-clockwise anti-clockwise direction, you can measure from PSE to this B dash in anti-clockwise direction, that should be DA, and this from PSE to A dash you can measure, that should be DB. So this way we can measure. So you can follow this clockwise direction, because everything we measured in clockwise direction, so there is no need of any confusion. So you can follow the clockwise measurements. So that's the distance and step length and step distance design. So this way we can design a single step using Smith chart.